Alright, so just to talk about the plan before we actually do anything, because we're going to be changing the plan a bit, just so everybody knows. Today we're going to be talking about inserting, updating and deleting data. We're actually going to be skipping all of this because it requires having actually learned about Node so we can interact with the database, and we have not learned about Node yet, so that can be a bit difficult. And then we are going to be looking at data definition language. We are going to go through that today. That'll probably be relatively quick. And then we're going to be looking into actually things like this, primary keys, relationships, and everything that entails, which means that we'll actually be going through two half lessons today. And then the last halves will actually be moving, if I can get away with it, to somewhere in the Node module, which means we'll be starting the Node module next time, and not the next time again as originally planned. And then we'll be doing the database module at some point during that. So now that everybody knows what we're actually going to be doing and not be doing, let's look at some actual things. So first thing first would be actually inserting data into our database. We did look at it very, very, very quickly last time, but there's a lot more to it than just, well, there's actually not that much to it. It's basically, at some of the last code we looked at last time was basically this. So what we do is write insert into the name of the table, which, as you see, we have it over here on the left. That's the user table. What columns we want to actually insert something into. So we can see we actually have 4 columns available: ID, name, email, and phone. But we're actually only inserting in name and email, which means the rest of them will be left as null or whatever is defined as their default value. How to change the default value, we'll be looking at that later on today. Then we write the pairs of values we want inserted. So in this case, I want the name to be set to washclothes and the email set to foo@bar.com. I can add more pairs of values here, so I can do clean dishes and then bar@foo.com, because that's a totally different email. And that means that I can actually insert 2 sets of values at the same time in one statement, which is useful if you want to bulk insert, for example, because doing an insert takes a bit of time in the database, because you need to verify that it has been written to disk, that it's no longer lost, that it doesn't break any references, which we'll be talking about later. So it needs to do a lot of confirmation, but especially the I/O, actually talking to the disk to save the data, takes a while. I mean, like 1 millisecond. But if you end up doing like 1,000 of these, if we only insert 1 value, you'll be using a second. Whereas if you just did 1,000 of these pairs, then that would only be 1 query, and it could probably batch all the I/O to the disk, so it might only take 5 milliseconds, which would be considerably faster, according to all known maths at least. In some dialects of SQL, it is actually possible to insert using a query. So we can do like this from user. But that won't work in, for example, it won't work here in MySQL. You can see it's not actually allowed. So that's a good trick to know, but I would say I have very rarely seen it used. So that's basically what's there if you want to talk about inserts. Next part would be talking about updates. So if we just query out what we have in the database, or in the user table again. So we have all of these things. So I have a couple of these, just comment out this. So I have a couple of these that doesn't have a phone number right now, which is pretty, we kind of want them to have some sort of phone number. So if you want to update the table, we're going to be looking at a couple of things, like how to fuck up all your data really, really bad, really quickly, which is my favorite way of doing it, and learning what not to do. So if you want to update something in database, you write update, the table name, if I can actually remember the syntax for this, update set user.phone equal to 1, 2, 3, 4, 5, 6, 7, blah, blah. 4, 5, 6, 7, 8, 9, 10, 0. Boom. There's a phone number right there. So if I just do this, we're gonna have a tiny problem.
All the phone numbers going to be the same.
Yep. It'll even tell me that I am not allowed to do this. So let's turn off safe mode. I assume we can do that somewhere. Preferences, SQL editor, and reconnect. To safe mode. Where did they tell me that this was? It's always fun finding these settings. There we go, save updates. As you can tell from the name, there's clearly a reason why we have it. But because we're learning. Oh, and reconnect. Makes sense. Close connection, reconnect. And let's try again. There we go. Now we updated 15 rows. Which sounds suspiciously like the amount of users we have in the system. So what it just did was that it set all the phone numbers to the same value, which is clearly wrong, and also why the safe mode usually prevents you from doing this. But what we really want is we want to update just one of them. In this case, I want to update the one with ID 13 specifically.
I have a question here very fast.
Yes?
After you make this mistake with updating, can you go back?
Nope.
No.
Your data is fucked, basically.
Unless you have replication and then.
No, if you have replication, all your data will now be fucked across multiple servers. You need a backup.
Backup, yes.
Yes. Replication just means that you can fuck up multiple servers at the same time, and it'll be really fast when doing it, which is usually not what you want. But what?
Fun.
I mean, I have only once did this to a database with 50,000 rows.
Ouch.
Yeah, that system basically had to be deleted and reinstalled. Yeah, it was a dev system, so no harm done, but you learn it the hard way. Yes. So if we want to update something specifically, well, we need to tell it to find something to update. So we do where, for example, we want to update specifically on the ID. So I only want to update where the ID is equal to 13. So if I execute this, it'll tell me that one row, and only one this time, was changed, not all 15 of them. And I can query again. And as you can see, specifically, the one with the ID 13 changed. Nothing more, nothing less. As you can probably infer from this, that means that anything we can do in a where, we can do here. So we can technically do where name like a%. So now we update all of the ones that has a all who have a name that starts with A. Execute, and you can see it updated 3 rows. And we go again, and all the ones that starts with A actually have a new phone number. So whatever you specify in the where clause for when you update is what will be touched. And if you don't specify anything, it'll update all of it. Which again is a really good way to blow up your production system, so don't do this. And last thing we need to be looking at is deleting things. So you do that by saying delete from your table user. What do you think happens if I do this, based on what we just learned with update?
Everything.
Yep. So I'm not going to do that, because we need some user data. But what you would again say is where ID is equal to, let's go with 14 this time around. So we say, alright, delete that specific row, and it says one row affected. And we select out again. And as you can see, now ID 14 is now gone. And we can also, just like we did with updates, we can do this we can do an advanced where. So we can delete 3 rows. Again.
We can specify that just delete the phone number.
No, because that would be deleting the entire column, which you can technically do, but that's changing the whole table. You say that with a table, you say my data looks like this, all my data.
You know what I mean? Like for example, in
so if you just want to set
Donald Duck, for example, I want to delete his phone number.
Yes.
No, if you just change his name to Donald Trump.
So what you can do is, so you can say, all right, set user.phone is equal to null, where user.id is equal to 11. It did not like that. So what is it not liking about this? Okay, semicolon in the wrong line. And as you can see, then it became set to null. Mm-hmm. So if you want to do something like that, you actually update the existing data. Because you're changing the data. If you say delete, like that is removing it. Gone.
No, in the previous example, the one that you change all the phone numbers to the same, then you would use that syntax. Let's say you select something that's null to change the value instead of changing the value for the whole.
I mean, you could, yes. My recommendation for you is to basically never use a where query that doesn't specify an ID. In basically all cases, that is the only thing you need. You need to update a specific row. If it turns out that's not the case, you likely have an error in your data model.
Okay.
Because usually when a user comes in and they want to change their name, it's only that specific user, and you know by ID which one it is. So my recommendation for you is always have a where clause that looks something like this, because otherwise you are going to fuck up something you didn't intend to fuck up at some point. And usually you would have gotten the ID from an earlier query, because you need to verify that it's actually there to update. So you will have it in basically all cases. Unless you're doing some really, really advanced, where you're doing maybe a custom programming language to make SQL easier to write or something crazy like that. But that's a whole other. I think that's pretty much outside what we're going to be talking about for this course. So, any questions for inserts, updates, and deletes, other than what we have talked about? Nothing?
All good.
All good? Perfect. Then, as mentioned, we're going to be skipping all of this. Then we're going to be talking about what is called the data definition language, or the DDL, as some people abbreviate it. We're going to be talking about creating tables, altering tables, and something called indexes. So, first thing, creating tables. We actually looked at that really, really quick last time. Can I close this thing? Yes, there. So, if I want to create a table, I do create table, and then Rasmus table. Now let's just call it students, because that's a better way. What we do here is, now we can create a table that have no rows, but that would not really make sense, because what's worth is the value of a table that you can't actually store anything in. That sounds kind of ridiculous. So we need to specify, well, what should we have in that table? And basically, there's one thing you always start out with, as also mentioned last time. You start out with an ID. A recommendation is to make it an integer. Because then we have something that can uniquely identify each individual row, and that will really never need to change. Why we need the ID kind of goes into the discussion of what is a primary key and what's a foreign key and things like that, which we will get to a bit later today, but I think we'll do that after a break. But for now, just assume we need an ID, and we need it to be auto increment, which means that every time we insert something, it should create a new ID, so we don't use the same ID for all users, which would be kind of ridiculous. Then we need to specify, well, what properties do they have? So our students, well, they all have a name, which would really make sense that it is a text. Some books you'll find will recommend you do use these things called varchar, but don't, because like usually you're going to be wrong. If you pick in just 30, I can personally tell you that my own name is longer than that, so that'll break. You can pick something really, really ridiculously big, like, but again, then what's the point? Use something like text, which are very wide. They can fit like a name that's 2 gigabytes long, which is a lot.
4 billion bytes, I think.
Yeah, that would be 4 billion characters.
Yeah, something like that.
No, 2 gigabytes would be 2 billion. We're not talking about 38 bits or 32 bits. We're talking about 2 gigabytes, right?
No, I just remember seeing somebody was explaining there are like 4 different type of text.
Yeah, they're like when you get into the nitty gritty of what all of these different kind of things mean, it gets really horrible. Other people might recommend you to use something called char, which you can also specify the length of. The difference between char and say something like varchar is that in char there will always be 100 characters. If it turns out that the name you inserted is not long enough, it'll just put spaces in front of it. So when you actually pull it out, you'll get, if you put in like Rasmus, you'll get like 94 spaces and then 6 letters. Yeah, and some people argue, but then it's faster searching. Yes, but we're not going to be, excuse my French, fucking searching for the name. We're going to be searching for an ID in most cases. And even then, we'll create an index, so we'll not be searching directly in the data. Varchar is a bit smarter. What it'll do if I insert Rasmus in there, it'll say, all right, we're going to be inserting Rasmus, we're only going to be using 7 bytes, not 6. Because it needs to also store how many bytes we actually have stored. But that means we won't get all those wasted space characters, so it'll actually fill less on disk. But it also means that when you specify 100, it'll actually technically be limited to 99. So it'll be limited to 1 less because it needs to also store the length of how many you have. And I think if you get over a bit in length or a byte in length, it'll actually start taking up another character. And knowing all these nitty-gritty, horrible, really horrifying details is just really annoying. So just use text. Makes your life easier. It'll probably be correct. And you'll have space for a very, very long name when you get in, what is his name? Any of you watched that kids show with Cody and Zach, that The Sweet Life, I think it was called? There's like a waiter in that name, at that hotel, who has a name that's like pages long. It's crazy. And he'll also fit in here. Let's see if I can find it. Sweet Life, I think he's called Esteban. Full name. You can clearly see we're not the first one who has searched for it. So where did it actually put me?
Right.
I think it's confusing me because I have it like this. Doesn't actually show it here. But it's something basically like this. Esteban Julio Ricardo Montero de la Rosa Ramirez. Which, if you just specified 30, you won't even be able to get his first 3 names. So just use text. It'll be correct. What we can also specify is that, as you saw in phone number, we could actually put in null, but we don't want people to not be able to specify a name, because we need a name so we can refer them and tell them that they owe us money. So we can specify that this should be not null. This means that, well, as the name says, this cannot be null. There'll always have to be a value. If we don't insert a value, it'll give us an error. And it still allows an empty string, but that's also technically a value.
Yeah, but let's say we can do that in the database, but even before the data gets nowhere near the database.
Yes, we should check that.
You have the validation on the page that they
Yes.
need to get passed to.
Yes, but I can disable your JavaScript. So
Yeah.
you should also validate on the server.
We're talking about normal users.
Yes, but usually hackers who want to fuck your shit up are not normal users.
I understand.
Like, they will know those tricks. They can just go in there. Like when we bought these caps when you get a student, they had like these golden emblems or letters you could get on, which cost 25 kroners each, and there was a limit of 4. But that was just specified in the HTML, so you could just go in, update the page using the Chrome Inspector, remove that limit, and you could add in as many as you wanted. I'm not sure what would have happened if I had ordered that, but I kind of wanted to just to see what they were going to do.
I was messing with that with credit scores in the US like 15 years ago.
Yes, and security hasn't gotten any better since then.
No.
So the benefit of doing it here, doing it in your server, and doing it in your client is what we call defense in depth. So if you have done it on the database, then if a developer forgets to check it in his code, at least the database will error out. And if some idiot, me, disabled all the validation in your browser, then at least your server will tell me that, no, that's not allowed, what you're doing there, fuck off, and give me a proper name. So you do multiple layers of these, because if someone gets past the first, they'll hopefully be caught by the next. And it also just makes it easier to understand, well, what is supposed to be in here. So what else can we specify on student? Anyone want their age in here? Cat chose for us, that's excellent. And would it also make sense that we say that the age is an integer, saved in how many years you have, or have been, are?
Age in parsecs, maybe?
I mean, they are, you actually have, I think you have a times...
Timestamp?
No, there's a lot of different data types. Some databases have a time span as type, so you can actually say between this duration, so you can actually specify how old people are. But let's look at that. Let's just for now say it's an int, and then look at an example of why that's a really, really bad way of doing it.
Can you also, when you do an int, can you put like a character limitation, because the max you can have is 100.
People they live for 150 years.
But it's still 100. You can't live for 1,000 years. So
but you can. What do you say? Say if we have int, like for age, it would probably be better to use something like a byte, which is smaller. Or I think in this case they call it an int 1, I think. But what we can, I think it's called check. So we can say here that, well, age should be less than 100, and age should be more than 18, because we don't allow people younger than that.
Yeah.
I mean, it doesn't necessarily need to be less than 100, because you can.
Yeah.
You can have
like pick a reasonable number here, of course. Like if you're doing 250, it probably might be a bit too much.
Yeah.
But like but we're going to be going into why this will not actually work, and why this will be a problem, because I can fuck this up really, really quickly. Other than just giving you the wrong data, and you will also notice why sites ask you for your birth date, not your age. So let's create this table. Let's fire it off.
How about the student ID?
There can only.
From the ID, right?
Let's just 2 seconds.
No, not really.
So you should actually keep your student ID if you have one. Keep it separate, because and that should actually be a string. Because if this ever change, which it might get if you get to a new school, you might get it revoked for other reasons. For example, like someone stole the ID, they might actually be able to revoke it in their system. So lots of different things, because what's really important is that your ID itself should never be part of the data. And this is where a lot of academics will hate me for saying this, because they say that there's something in your data that should always uniquely identify you, but that is wrong. And that's a really good way of suddenly having very wrong data in your system. Because if I used your student ID and it suddenly changes, you get to a new school, well, suddenly all my data, some of my data about you is wrong, and then I need to go in and update the ID. But what about all the things that refers to that ID? I might have some class lists where you are actually where that ID is referred, and now we need to go in and update it. So it's easier just to keep data and IDs separate. Lot less headaches, and it generally tends to make everything faster.
But are you talking? Are you talking the? I suspect that she's talking about the column that says student ID.
No, it's really the student ID that you can
This-
see in your ID register.
Oh, okay.
2011,
Oh, okay. Because I thought you were referring to the earlier exercise where you have the ID and then you have the student table, and then the student ID it's actually a foreign key to another table.
Just one moment.
I
I
think
would
in
assume
that
you're
case,
talking about
except
something
for
like
her-
this.
Yeah.
Yeah. It's part of the student ID itself.
By speaking for the ID, what we make it like a primary key.
Yes. And
It should be just numbers, or can be like mixed between numbers and.
it can be anything. Like the name could be the primary key. But once we get a bit later, we'll be talking about what a primary key actually is, and together with something called foreign keys, which is a thing that, like, at least for me to understand foreign keys took probably 2 years. But that was also before I had any formal education in databases. So, but I hope that will help you actually understand it. So if we try to run this again, we should get, yay, no more errors, 0 rows affected. Awesome. And then if we refresh out here, we should see our new student database that has an ID, name, age, and a student ID. So what if we want to insert something into it? So insert into student. We want to set the name, the age, and not the student ID, just today. So we're going to go with the student name would be Ricardo. He's going to be our sacrifice today. How old are you?
I'm 25.
Question.
Yeah. I mean, you don't have to tell us the
many
truth.
years ago?
So
I was 25 in 1964.
yeah, that's fine. I mean, I don't care if you're lying to me. It's only yourself you should feel bad to.
I don't lie to anybody, just to myself.
I mean, I usually go with 25 plus taxes and that and all those others.
Plus mom.
25.
Yeah, all that shit.
25.
25 is actually when the odometer broke.
Yeah. So all right, we inserted Ricardo in there. That's fine. Then let's insert evil Ricardo. Evil Ricardo will try to break the database because he's evil. So he's 1,000 years old.
Yes, that is correct.
And we just talked about that. We don't want this to work.
Remember,
Yes.
I began as a flusher and I ended up as a Master Yoda. Remember that.
So now you can actually see it says here, well, constraint student.age failed for hack your future.student. And remember that we specified when we created the student table that the age were only allowed to be a max of 250.
Yeah.
And that's exactly what it's doing right now. It is verifying the data. So we can set up things like that even if the data structure itself would technically allow for something more. We can set up custom validations. So again, more of that defense in depth.
If you put 250 there, that would.
I think that won't actually work because I specified strictly less than. Yeah. So I think 249 because that's clearly much more realistic. Then we got it inserted. So now if we select star.
So it doesn't. Because you put it less than 250.
Yes.
Okay.
I could have specified less than or equal. So now as you can see we have Ricardo, which is 25, and evil Ricardo, which is clearly not 10 times as much.
That sounds about right.
But alright, that student ID column. Well, it turns out for the data so far we don't really need it. So what if we want to remove it again? Then what we can do is, well, as it also says that we're going to be talking about here, is altering tables. Now we have learned how to create basic tables. Now we need to change them because we clearly turned out that our initial assumption about how the data was wrong. Ricardo doesn't have a student ID anymore. So we can do alter table and then alter column. I think it's just actually called drop column because we need to remove the column itself. Or maybe not.
Delete column maybe?
No, it is called drop, but alter column, student ID. This is also one of the things where MySQL remove column, where the databases do not agree on how the syntax should be. So there's add some more, remove, drop. So zoom out here a bit. So it is called drop column. What are you talking about, MySQL Workbench then? Drop column student ID. It's because I need to specify the actual table to alter. So when we want to do this, we need to specify, well, what table are we actually working with? Well, in this case, we're working with the student table specifically. And I want to remove a column, so we say drop, which is the general SQL name for when you want to delete something that's not data. So if we just execute this, run it, then it will say down here, all right, everything worked. And then we can select star from student. And as you can see, we don't have a student ID column anymore. We can also go the other direction, so we can alter table student add, if I can spell, add column, and let's call it evilness, because Ricardo needs to score max in that. Which should be an int, and it should have a check. Can we not specify that here? Oh, we cannot. So for now, I think we can just specify this, and then we have to add in the check later if you want that. So alter the table again, boom, that also ran. We can select, and as you can see, we now have a new evilness column, if that is what we were going to be working with. And lastly, we can also change the name of a column. So alter table student, update, student, update column. Was it just alter column? Rename. Change column. Of course, because that makes a lot of sense. So again, as mentioned, this is where different database systems do it kind of differently. So change column from the old name, so evilness, into goodness, because that's much more representative. What does it not like about this? Old name, new name. Oh, and we should also still tell it the type, so it's still an int. And then we can run it, and it ran successfully. And if we then select everything from the table, it now says goodness. And if we had data in here, that would also be changed. It wouldn't throw out the data. What happens if you then change between things like different column types? I don't actually know. I wouldn't recommend doing it. The database is probably going to do its best to make it work. And I assume if it fails, it'll undo the entire change, which is a kind of useful property of databases, is that we can tell them, do all of these changes or none of them. So even if just one of them fails, just roll back everything, stop, hold, revert to a good known state. So we don't get half broken data in here. So last thing we need to talk about is called indexes. And like, I can't really show you that much of a benefit of indexes, but we can at least look at how to create them and talk about theoretically what they're supposed to be good for. So I think if we have an existing table, it's alter table student something index on name. So basically just working with error messages here until we get something that compiles. Specified key was too long. Okay, so that was a really bad example. Let's just add it on the H instead, because that does not have that limit. So right now we just did something, and if we run the query, we'll notice that absolutely nothing changed. So what's the purpose of an index then? Well, an index helps you if, say, we have a where clause where we say where age is more than 20 and age is less than 200. Then the index would actually speed up this query for us. More than. But because we don't really have enough data for that to happen, it doesn't make that much of a difference. Indexes are really, really good when you end up having like more than 100 rows, and especially when you start having millions of rows, they get really, really critical for things to work. And in some databases, if you want to query on something, you actually will need an index for it. So the difference is, well, what does the database do if it doesn't have an index? If it doesn't have an index, it just goes through every student. Is your age more than 20 or less than 200? Awesome, you're good to go. Next, is your age less than 20 or more than 20 and less than 200? No, you're not good. Next student, and it asks again. And as you can imagine, if we have a million rows, this will take a while.
Yeah.
Because asking a million times just takes a moment, and it needs to load all the data from the disk to actually be able to look at it.
Okay.
But what it does when we create an index is that it kind of creates a structure the other way around. So I'll try to illustrate this with some Excel, but I think it's really going to be kind of difficult.
One of the Linda's videos
That we have selected
was on the list for us to see. The guy mentioned it like an index. It's actually it doesn't go into the tables itself. The index creates a table.
Yes.
Where it looks
Yes.
that one, and then it goes from that one to pull the record.
Exactly, and that's also what I was kind of trying to show you here, because you can kind of imagine Excel as a table, like as columns and rows. So if right now we have a table that goes something like this, so it has an ID, a name, and an age. And you have 1, Ricardo, and 25, 2, evil Ricardo, and 249. And if we ask for the age, you'd have to actually check all of them, because if you don't have an index, it only have an index on the primary key. So, well, what does it do when it creates an index? It actually creates a table kind of the other direction. So it goes age 25, and then 249, and then it says, all right, for 25, we basically have someone with ID 1. And let's just, for samples purpose, let's add another one, Ricardo 3, because I'm clearly original with names. And then we also have someone with ID 3 here. Okay, good. Then with 249, we only have number 2. So it says if I ask it for those ages, it just goes, all right, so find all the ages that are between 20 and 200, and it says, well, 25 is. All right, 25, so which ones do you actually point at? Well, I point at this one. And I point at number 3. All right, that's easy to look up, because it already knows where those are on the disk. And it then does a lot of magic to actually make this really work. I'm kind of trying to illustrate it here without going into all the details of how it does behind the scenes. But that's the basic idea.
Does it do that for every single row and column?
No, you specify what an index should be created on.
Okay.
So as you can see here, I'm actually specifying parentheses, because I can specify that the index should be created on multiple columns. And then if I do this, for example, and run this, you see it runs through just fine. But what it'll actually do is it'll create one down here called age, ID. And then we'll have, all right, for 25 and 1, which is this comma, we have number 1 that matches. For 25 and 3, we have number 3 that matches. For 249, comma 3, comma 2, we have number 2 that matches. So that means if I ask for something where the age is less than 200 and the ID is more than 2, it can quickly look up here, rather than having to scan through all of these and say, are your age more than 25 and is your ID more than 2? And that's basically how it does it. So it can speed up your queries quite a bit, and it does a lot of advanced stuff. It doesn't just create a long list like this. Sometimes it actually basically creates what we call a tree, but that is really advanced, and we can talk about that for 2 whole lessons, just how an index tree works. So let's not do that here. But remember, you want more speed, use indexes. But if indexes are so goddamn fantastic and make all our queries faster, why don't we just add indexes to everything and all the combinations that can possibly exist? Because we can do that. And so space is one reason. Anyone who can think of another? So if I need to do this index, I actually need to write down what's the data. So every time a new thing comes in, I need to actually go and update all my indexes, which means that my inserts and updates will now be slower. So you're sacrificing write speed for read speed, which actually quite a few cases makes a lot of sense. And that's also why you should try to balance out, well, how many indexes you have, because like only create the indexes you need. The ones you don't need to read from, well, they're just a waste of space and a waste of time to keep them updated in the first place.
The application will determine the kind of index you need to.
Nope.
Nope.
Oh, yes, the application will determine which ones you should create, but you'll be looking at that while you're kind of making your application.
Okay.
There are some database systems who can just look at which queries did you make and say you need the following indexes, and then just like, okay, and it creates all of them for you. Which, like, that's fantastic. Just don't wait for your production to be too slow, because when it's creating the indexes, it just freezes the whole database.
Of course.
So then you can't do anything at all. You can't insert, you can't read. You just have to wait for it to finish creating that index. And like for some systems, this takes a while. Like I think I read something like eBay, they had a problem where they needed an index on something, but they had 200 billion rows. So if they had to create that single index, that would have put them offline for a month, which would be not fun.
Can it be done in sections?
Again, depends on the database system. What some databases allow you to do is say, start creating an index, but don't use it yet. So it's just does it in the background until it's ready, and then all your queries will just be slow because they're not using an index. And then once the index is ready, it'll switch to using that.
Okay.
So it depends very much on the database. I'm not sure what MySQL does.
The other question I would have is like this: okay, you create a database and you create the index, right?
Mm-hmm.
But let's say you're creating a new Twitter, a new Facebook, where all of a sudden you have gazillions of users inserting and updating, and at the same time you set up the database to create the index right from the beginning, so you want to catch up.
Mm-hmm.
What would happen in that case? Because now the whole thing is going to be slow, because now you have.
What Facebook does is they don't use a normal database. Same thing with Twitter. They have so much hammering their systems that it is basically impossible for them. So they do a lot of advanced stuff where they actually like Facebook. I think they have 100,000 running instances of MySQL, and then they have a whole layer on top that delegates to the correct database instances. And then for reading and searching for data, they have a completely separate database that they just update later. So once you actually create a post on Facebook, they'll create that post in the database and you can see it, but your friends can't see it yet. Then they have something running in the background after they said, yeah, your post is created, that's fine, but you don't know if your friends don't see it yet. So what they then do is on the background, they copy it over to the databases you're actually reading from, and they then can be read, and then they can have a lot of those ready. So like going into the scale they're working at, it just gets ridiculous what you need to do. There's a rule of thumb that says every time you increase your user base by about 10 times, so when you go from 10 to 100, it's not that much of a problem. When you go from, let's say, 1,000 to 10,000 or 10,000 to 100,000, you need to re-architect the entire application. Because basically all the assumptions you made are wrong. And that happens every time. Because when you're just figuring out, can this application actually earn me money, you don't really caring about being able to scale to 1 billion users. You just want to earn some money so you know if this is a good idea or not. Because scaling to 1 billion users, if you have that problem, you can also afford to hire more programmers to solve that problem. But if you're just trying to figure out, well, do they actually even want to use my new chat platform, Slack 2.0? No, they did not. Well, then it's probably a good idea that you didn't spend 10 years architecting it to 1 million users when you can't even get 10 of them. So
that makes sense.
Like,
that's a classic case of failed startups.
Yes. So, like, rule of thumb, only create what you need. And like nowadays, there are things like Azure Cosmos DB, where you throw in data and it indexes all of it. However, what they do that's actually pretty smart is they don't make any guarantees about you being able to read it after you insert it. They make a guarantee.
What's the point?
No, but listen. They make a guarantee that when they say, yes, I got it, it will be there. It just might not be there right away, but it will not be lost. So they have something that's called eventual consistency, where they say, yeah, we got it, check. If query for it, it's not there. And then after maybe 5 seconds, it will suddenly be there, because they're doing the indexes in the background, so they don't slow down your inserts, and that actually allows them to have multiple instances of the database running, because they don't need to synchronously wait for all the database to say, yes, we're ready.
Okay.
Just one of them just needs to say, yep, I got it, and maybe a backup that says, yep, I also got it. Then they can say, all right, we're safe. We can risk losing an entire server now, because it's on at least 2 different machines. And then that basically copies out to all the other machines. So if you wrote to one machine, and then right after you query, but you actually hit another machine, then that machine doesn't have it yet.
No.
But it is
which
safe.
One is that? Which system is that?
That's Azure Cosmos DB, but that's the rule for any system which is called eventually consistent.
Oh.
So what databases do is they make kind of different level of what we call consistency guarantees. Relational databases like MySQL and Postgres and MS SQL, they make what we call strong consistency. If they say they saved it, it's ready. Write that. But that also means they'll be slightly slower at saying that it is ready, because they need to guarantee that you can actually get it back. And if you have, say, a cluster of them running like 10 machines, it needs to be sure that all 10 of them will actually return the result if they say that this is ready. And that takes time. Like, if you need to coordinate 10 machines, like imagine coordinating 10 people, that takes more time than just telling that, yes, it's ready, and if you're the only person who needs to verify it.
Yeah.
And then what Microsoft then does is that they allow you to have different consistency levels for Azure. So you can have the highest strong consistency. That just means that it'll cost more because they need to throw more machines at the problem. Then you can go down to inconsistency. You can say, like, the same connection can guarantee that they can read it right away. Which would make sense in your case. If you're posting, you will also be able to read your post right away.
Yeah.
But that still only means that the same server needs to guarantee it, because you're only connected to one server at the same time.
Yeah.
Then you can decrease it further. You can say, nah, I'm fine with it just being available at some point. And that means, like, you can just write it, and then they can really quickly say, yep, we got it, even though they haven't actually done anything with it yet. And then they can start updating all the things they need to behind the scenes. So I think they have another level, but I don't remember exactly what it is. And this goes for most database systems. There's basically something called, now we get into really computer science, there's something called the CAP theorem that says that a database can only guarantee you 2 out of 3 things. So you have consistency, which means do you see the data when you wrote it? They have availability. What happens if we have multiple databases and they suddenly cannot communicate? Or one of them dies. And I think, there's availability, and then there's partition tolerance. So partition tolerance is what happens if the databases cannot suddenly communicate, but we can communicate with both of them. So what happens with the data in that case? In your MySQL, it will just say, I can't accept any data right now because I cannot confirm that it has been written to all of them. Which means at least you won't lose any data, which is really what they guarantee. They won't lie to you ever. You can also say, nah, we sacrifice availability. That's fine. It's okay for us that the entire system goes down. That's basically what MySQL does. If it partitions, it just says, all right, we're dead. Can't do anything more. You can sacrifice consistency, which says that, all right, it's fine if we can only talk to one machine and that the rest of them will be updated at some point. And that's fine for our system, which would make sense for something like Facebook or Twitter, because it's fine if your followers don't see it right away. But in other like banking transactions, you want this to be available right away. Because you don't want to say, but I can see that I sent it, and they say, no, I can't see anything yet. So then you want it to be consistent, but then you would rather have the entire system be down rather than telling you that they sent the money but didn't actually.
Is that why they usually bank systems update overnight?
No, that's because banking systems are usually made on mainframes from the 80s. But that's a more, because they're just really slow. They're written in, you have probably heard about this thing called COBOL.
Yeah, COBOL.
Yeah, if you can write COBOL, you're going to be really, really rich. Because that's what all the banking software is written in nowadays, still. And there's no one else who can write it, so they will happily pay you a couple of millions per year to maintain it. Because that's cheaper than rewriting it. So, if you want to be rich, go that way. You'll hate your life while you're writing it, but it's a really quick way of earning yourself a Ferrari, if you're feeling that way. So, let's go for a 15 minutes break now.